and Thibaut and I are on there. And so we really love to hear what people want to see out of the Planktoscope and really how we can make this better. Thanks again for everybody for coming. This was really fun, and I'd be happy to take questions you guys have about Planktoscope or plankton in general.
Thank you very much, Adam. It's really fascinating, and it's fantastic to see how much the community has grown, really. So I knew that a lot of people had made it, but the numbers that you were presenting now, they're really impressive.
Yeah, I don't know Slack. It's hundreds, but it's always increasing. So I really encourage everybody. I'll kind of go back.
Yeah, I mean that's the nature of these kind of instruments, I guess, that you don't also know all the people who actually made it. So there are probably many more out there.
Exactly. There's probably hundreds more that we don't even know about.
The floor is open for question. So the main Pablo already has a question. Fantastic. So let's start with you.
Thank you, Tobias. Thank you, Adam. Great presentation.
Thank you.
Yeah. I would like to hear your thoughts about when an instrument like this when is the time to share it? I mean, you develop something and you feel it's not ready yet, and you want to keep it yourself for a while, and then after that you want to share it, but you don't want to share it if it's not ready or it's going to be like a problem more than a solution. On the other hand, if it takes too long, you are missing opportunities or getting help from the community. So any comments about that decision that you need to make?
Yeah, so this was something I also was nervous about. So being a scientist, right? Again, when you're putting up data that is very important, you still need it to be of very high quality. So I think with the microscope and when you're looking at microscopic images, the intercalibration was the thing that scientists that were using the machine were most concerned about. But I do think that through sharing it very early, right? So this project was open from its inception, right? We were kind of showing it as we went along, and it was honestly incredible. We just published this paper, which didn't have a guide. We had the plans and the software available, but a few people were able to put it together without really any kind of intense or comprehensive guide for putting it together. And through these people, we actually got the first really great comments in, okay, well, you should think about this. The lens assembly needs to be, much more stable so that we can get these images. Again, when you're dealing with conjugated lenses, you really need to make sure that the magnification is the same from object to object. And so I think for us, opening up early was really essential to getting the images to the point where they were actually intercalibrated and of scientific quality. And the people using it actually, so Fabian Lombard, who is a wonderful plankton researcher in Villefranche, was amazing in that he built, heroically the first few instruments, which again were, buggy to say the least, but he was able to tell us exactly what we needed to do to get the images to high quality. And then again, through Ecotaxa, which is a really wonderful community itself, we were able to upload the images and people were able to critique these and give us great feedback on how to make them better. And so I think it's great to open it up early, but yes, you do need people to give you really good critical feedback so that this data is of scientific quality. So people that are using it for important research, from different places all over the world can trust that data is the same coming, from California as it is coming from Croatia.
Right, thanks.
Yes. Who's next?
Ross, you have a question. Thanks for joining us.
Yes. So I'm interested in automating science. So I was curious, what do you mean by autonomy and what you're planning to do?
Well, so the idea is that we would like to just put the Planktoscope either on like an ROV or a buoy. So what we've done now is we've made kind of a rudimentary buoy. I'm working with a group at the California College of the Arts here. And so what we'd like to do is put the Planktoscope on the buoy and have it basically automatically taking images, say every few hours.
Is a buoy, is that in British English, a buoy? Is that the same thing?
Yes, I think BUOY. Yeah. So
Yeah,
a floating piece of a floating object in the water.
Yes.
And so what we have done is we've put the Planktoscope in a case that is waterproof. And we're working on getting solar power. Right now, you can run it off one of these kind of large laptop batteries, for several days autonomously. And so you can set this to take images, say take 1,000 images every hour for a few days. And then upload this data. And so the idea would be to give these some kind of network connectivity. So again, say what the dream would be is to have these buoys say throughout a waterway or a bay, and have it, always taking data. And that way you could have it send you a text message if it did find, Alexandrium at a concentration over something that's going to be harmful, and then let people know. Because right now, right, it is very robust and usable, but still it's relying on the user to, open up their cell phone and actually run the acquisitions. But it would be great if we can get these actually just running without people needing to be there while the things are running. And so I have these running now just on my lab cultures. So I have it running, just for experimental purposes to look at my culture health. You can have it run for a few days and taking images of thousands of cells, every half an hour, just to tell you what's going on in your plankton culture. But ideally, we'd have these in the field, right? So in these shellfish farms and in these places that are dealing with algal blooms. And so, yeah, that would be what we want, is making them, taking the people out of the actual experimental aspect, and having the data being automatically uploaded. So that would be honestly the dream. As well as the initial idea for the Planktoscope was to put these on sailboats, right? Because I told you these research vessels are extremely expensive, but there's thousands of people making transects every day on sailboats. The idea was, if you could have something that is autonomous, you could say have it running water, as you were going through, and take the people out of the experimental design, but taking images, in an automatic way. And so this is something we're working on, and we've actually had a lot of help from the community. People have a lot of good ideas on how to make this more autonomous. And so that's kind of the dream that we've been working on. And hopefully this year we'll have something working that we can get out to the community.
Okay, thanks.
That sounds really fantastic. I can only underline what you also said about opening up early. That's what I always recommend too, for many different reasons. So one is, maybe early people who are involved, they disappear, but they should have made contributions to the documentation that are difficult to do afterwards. It also accumulates more and more work. So when the bigger the project grows, the more difficult it is to start with documenting. You're missing out on early feedback, or maybe going another way. And also even the university, I think that in our university, I haven't seen that so much as an issue, but in sometimes when you have something that already looks really cool and finished, the technology transfer office might also come into trouble, because they say, oh, now you shouldn't open this, but you should patent it or something like this. But if it's always been open, it's not an issue.
Yeah, and I think, again, being open hardware and open software, we've gotten great feedback both on the construction of the machine, and as well as, all of this stuff is on GitHub. So people have made their own versions of the software that have actually made it much better, and we've kind of implemented these in. So opening up to the community is always, in my opinion, it's always great. And again, since the data is all on this open website, Ecotaxa, people can use data from other, right? Again, with science, it's always hard, right? Because it's hard to find the data. But if you put the data all out there and open, then people can use this for their own needs and kind of give you feedback maybe on your own project. So again, I think having these things open has made it, only better.
That sounds like a fantastic experience. Can you comment on a couple of and then Pierre, I see you raise his hands afterwards. But can you comment on a couple of technical things that you remember that actually improved, things that you maybe didn't foresee, or things you had to tweak? Because obviously this microscope uses a lot of standard parts, but where did you have to optimize to get a better quality for this application?
So I think, again, machining, we originally had this all out of acrylic, so people were laser cutting this, and people actually made it out of anything from, various plastics to actually somebody machined it out of metal. But again, with optics, right, we really wanted the optical train to be very robust. And so initially we had people with these M12 lenses. M12 just means the thread size is M12. So these are used a lot for like industrial manufacturing as well as surveillance. And they're very high quality, right? So we have these in like kind of a macro setup, which is also nice because then you essentially have a tube lens and an objective lens. And so by changing those two things, you can change your depth of field and magnification. But initially we were machining them and kind of threading these acrylic things. So getting them to be aligned was kind of a nightmare. So that was something through the community. People were saying, okay, this is too hard. I've never used a tap before. It's things are not looking good and the images are not looking great. And so through that, we actually, got a part that does that for you. So you thread that into a little piece of aluminum. And then instead of having to machine that, now that's one piece that you put in front of the Raspberry Pi camera. And then that part is no longer an issue. And various other things with the stages. So one thing I've gotten from a news lab is like magnets are amazing, especially for optics, because if you use strong magnets, they can keep things really tightly focused. And so again, we got feedback from having things that were originally just kind of placed, and we've put these magnets in that really tightly made that optical train very robust, and made the construction easier as well as more reliable. And so I think through the machining, it was really great to hear feedback on people constructing it. Because again, initially as well, we actually took inspiration, honestly, from IKEA and from these well-made guides for putting things together. Because initially, say if you skipped a step or something, you would have to kind of go back 6 steps, you know, and put the camera in, or if you forgot to put some lens in. Whereas now it's really straightforward, and Dav has done an incredible job. And now where it's very straightforward, and so we've actually had people that had, you know, no experience in making or electrical engineering put together the kit in a few hours and take images that have been validated by, you know, our Plankton researchers on Ecotaxa. So that has been a great part, I think, in just getting the iteration of putting the machine together. And the software is like a completely different story, but we've had a lot of help through a lot of very fantastic software engineers saying, okay, this can be made better in this way. And like, this doesn't make any sense. You should do it this way. So that has been really great. So both the hardware and software, again, have been great to iterate through the community.
Thanks. Pierre, you have a question?
Yes, so thanks, Alan, for
Yeah.
your talk. So could you comment more about how you take the images from the sample? Because I know that you have a container with the samples from the ocean, and then you have like a small pump, and you infuse the sample through a vial, maybe, and then you took this picture. So these pictures are taken while the sample go through the vial, and so that means that you have emulate a kind of high-speed camera with the Raspberry Pi, or how it works?
So right now, because of cost reasons and performance, right, we're just using the high quality Raspberry Pi camera, which is honestly very amazing. It's like a 12 megapixel camera that you can get for, you know, less than $100. And so what we're using now is a stop flow strategy. So with this setup, right, what you will have is normally you'll have like a conical tube, which is actually where you load your sample. And so what most people do now is you do concentrate it in some way. So you either, you know, you do a plankton tow or a Niskin bottle or something, and then you load your sample in. You know, if you are looking at this in, you know, a robust way, through that concentration factor, you can then like back calculate, you know, bio volumes that you've done through your tow. And so what it does is you load your sample in this vial, and the peristaltic pump will pull it through. And what we're using now is these inexpensive glass capillaries. And so in this way, that's also modular. So right now, we're kind of optimized for most phytoplankton, which is like 20 to 300 microns. And so this glass capillary is 300 microns thick. And so what it'll do is pull the sample through. And so you'll say how much you want to image and how many images you want to take. And then what it'll do is the pump will run and then pull the sample through and then image that glass capillary and then store those images on the Pi. And so then in that way, you'll get all these raw images on the Pi. And then you could run, you know, several image acquisitions. So you could run through, you know, hundreds of mils of your plankton tow, and then afterwards run that segmentation on that sample. And then you can get those objects out of there. But yeah, right now it is a stop flow system. You could use, say, like a global shutter camera, but these are much more expensive, and they tend to be a much smaller sensor size. So this was the strategy we think was like cost efficient and also getting us very good images.
Okay, thanks. And today, the Planktoscope, how much time you need to process the image?
So I can't remember how many. It honestly depends on how many objects you have in your image. But you know, I wish I knew seconds per image. But yeah, it really depends on how many objects you have.
Okay.
But again, because we're doing this all on the Pi, we wanted people to be able to do this without any software. So again, with this, you don't need any software downloaded on your laptop or cell phone. You could run the segmentation completely on the Pi. So again, it is limited a little bit by the processing power of the Pi, but we are really excited because this new Raspberry Pi, the Pi 5, has a lot of very cool advancements in graphics processing and just compute power. So we think as this develops, we'll get this a lot better. As well as we're really excited right, we have like a very, I don't want to say simple, but antiquated way of doing the segmentation, right, through threshold. But now you can see through these open communities that are doing image processing, a lot of these cool AI tools and these segmentation tools, we could get a lot more sophisticated and more accurate in doing the live segmentation. And so this is something we hope will happen in the next year.
Okay, thanks.
Yeah, of course.
Excellent. There's also a question in the chat. So Gyrish, which is the nickname of the account, asks, is there a way to sort the sample to individual cells in your device?
So right now, yeah, we don't have like a nice flow cytometry way of doing it. I mean, you do have an outlet, right? So you can recover your sample. But yeah, it would be a dream to have it where you could sort things by size. And I think, again, with some clever fluidics tricks, I know you have done a lot of cool stuff with fluidics. It would be great to add that. Again, because one of the other dream projects we have is we have a lot of people doing genomics on the ocean. But again, what people normally do is you collect a lot of plankton, you smash them up, and then you sequence it. But what would be really great is if you could, say, use a machine like this, get images of the plankton, sort those or barcode those, and then get genomic data on those things. So I think, again, this is well within the community's grasp. And I think with a few modifications to the machine, we can get to this. But that's a great question and something that we're really excited about approaching in this next year.
Hi, Adam. Yeah, great.
Hey.
Great. We discovered this device a couple of weeks ago. We're really excited about it. So we're a research group over in Plymouth in the UK, and we work on aquatic embryos. So a lot of what we work on is actually encapsulated and benthic, if you like, but we do also work on sort of planktonic stages. So this sort of solves a big problem we've had. But I think another thing that's been really nice to see in your presentation is the journey, which is not dissimilar to ours. So we're using a Pi 4 and an HQ camera to be able to essentially the device for sort of long-term imaging of aquatic embryos. And we've sort of had the same thing, open source hardware, open source software. Lots of people sort of saying, well, actually, would you build one for us? And now we're kind of same thing, you know, sort of build, essentially kind of have a kind of commercial arm in some ways to what we're doing, just to try to maximize the impact. So so I guess there's two things. The first one is I see on your website that essentially you can kind of you can get a quote. So I'm guessing that's really to do with the fact that you can kind of choose, you know, in terms of magnifications and options in building an instrument. Is that right? You can also, right, there's, again, Periscope kind of came out of this necessity, like you just brought up. The community really wanted to, some people didn't want to build the whole instrument, they just wanted to have the instrument. And so you can, through Periscope, order the kit that comes completely assembled. So it'll come in a Pelican case with all the parts you need to kind of swap out all the flow cells, everything you need. So, you know, within an hour, you can then put this on your boat and start taking images. Also, you have the option of getting the kit, which I think is really great for educational reasons. And so you'll get that kit I showed you, which will give you all the components. And in that way, you can put it together in a few hours. And I think this is great. Again, from what I've seen when I'm on these research vessels, you know, you do have these great flow cam instruments and these IFCB instruments, but they're so complicated and there's often a lot of downtime just because they're not working, right? The fluidics is jammed or something's happened to the optics. And so I think through the process of putting these together, which again, it takes, you know, a few hours to put this together, but in that you kind of see everything that goes into it, right? And you don't have to be intimidated by kind of what's going on. And in that way, if something does break, you don't feel nervous about taking it apart and swapping out a part and then getting it back in action in a few hours. And so that's the different kind of quote plans, as well as, you know, we have educational pricing and kind of depending on what you want to actually use the Planktoscope for. But I think that's the main difference is the kit or the fully assembled. Yeah, and I mean, I think the idea of assembling is great, and it's kind of, I mean, that's what's neat about this kind of project. People actually understand how the device works, and certainly for teaching, I can see how yeah, how that could be something that we could build into the curriculum here, which would be really exciting. A sort of more specific question was around biofouling. So we do a lot of long-term imaging of embryos out in the environment,
Yeah.
and biofouling is kind of this recurring issue.
Yeah.
Have you thought at all about how you're gonna solve that if you do kind of get this into a form where you could deploy long term?
So again, yeah, I've imaged, environmental samples for, a week or so, and it's fine. Again, all you really need to do, what we've seen, like I've used the same capillary for, months, and what we just have to do is flow through freshwater. You really just have to do that after the acquisition, and that works quite well. These pumps are great, right? You can run them at, like 20 mils per minute. So you can flush through a lot of freshwater. If you get bubbles or something, you can run through like isopropyl alcohol or something like that, or some non-ionic detergent if you want to clean out the fluidic path. But yeah, the idea is, I think if we do have an automated machine, we will need a way to kind of switch capillaries if you do have some kind of thing. So we're thinking of like a simple turret system, which will kind of put in different capillaries, because these capillaries are very low cost and they're very easily assembled. You just have some Tygon tubing and actually just shrink wrap, and that kind of seals it in. But yeah, biofouling, again, that's something. Again, not my introduction to ocean research. Was really shocking to see how biofouling affects anything you put in the water is going to be biofoul. So yeah, we will, I think, need like either a cleaning cycle, so something where you would just flow through fresh water. And again, you don't really need bleach or anything like that. I think maybe if you were on, month-long deployments, then you'd have to start worrying about that. But I think a simple cleaning cycle with fresh water has been enough to keep these in action with the same capillary for several months at a time.
Yeah, I mean, that makes sense. We've sort of played with, wiper-based systems, but obviously that doesn't work inside a capillary. But the other thing is around sort of high pressure. So it's whether or not you can sort of generate enough of a burst of high pressure to just sort of clear out a tube. I mean,
that's a trick that we've done simply. Like if I do have a clog, simply what you have to do is really just pinch the tubing and then let it go, and that generates enough of a burst to flush anything out that was in there. And again, you can do a lot of stuff in kind of pre-filtering, right? So we have a 300 micron capillary, so we have a lot of these just simple sieves you can put in the way, and that really solves most of the problems as far as clogging. And again, these pumps are super powerful, and the fluidic path is robust enough where you can really flush out anything you have in there in a few minutes. Yeah, it's a great question, though. It's something that
brilliant. Yeah, great. Thanks for a great talk, and we'll be in touch.
Awesome. Yeah, reach out.
Well, thanks, Adam, for your patience to answer all our questions. I think it's really,
of course, yeah,
one of the advantage of the people that connect live, that we can ask you directly. It's a fantastic opportunity. So I've definitely learned a lot. I don't see any other question coming up. This is the last chance if you want to ask something right now. If not, there's always the online community and the webpage and the other users who've tried it. So it's really exciting to hear, and I hope that we can. I still haven't actually tried the Planktoscope myself. I've wanted to do it many times. I hope that we also get around to that.
Yeah, please reach out.
Once more, thank you very much, and all the best of luck for this really awesome project. I think that there's still a lot of potential there, and I hope that you'll have a good experience in scaling it and using it.
Yeah, thanks again. This was really fun.